The urinary system is best known for removing metabolic wastes from the body in the form of urine, but its importance goes far beyond that function. As the kidneys filter large amounts of blood plasma, they are well positioned to detect changes in blood volume and composition, and respond accordingly. In fact, the kidneys are critical in maintaining steady state, or homeostasis, of many blood parameters, including blood volume and pressure, osmolality, concentrations of various solutes, blood pH, and red blood cell count. Urine formation occurs in functional units of the kidneys called the nephrons. A nephron consists of two major parts: a glomerular capsule, or Bowman's capsule, and a long renal tubule. Renal tubules of several nephrons connect to a common collecting duct. Basically, blood plasma is first filtered in the Bowman's capsule. The filtrate then moves through the long winding renal tubule alongside a network of blood capillaries before draining into the collecting duct. This long passage is where the blood reabsorbs what is needed, and additional wastes are removed. This process determines the composition of urine and is regulated accordingly to the body's needs. The kidneys control blood volume and blood pressure by removing more or less water as necessary. Water excretion by the kidneys is regulated by a number of hormones, including vasopressin, also known as antidiuretic hormone, a hypothalamic hormone released in response to low blood volume or high plasma osmolality. Vasopressin causes the kidneys to retain more water by increasing water permeability of the collecting duct. Aldosterone, the salt-retaining hormone, secreted by the adrenal cortex in response to low blood sodium. Aldosterone acts on the distal tubule and collecting duct to increase reabsorption of sodium, which is followed by increased retention of water. The kidneys themselves produce an enzyme called renin in response to low blood pressure. Renin initiates a two-step process that produces the hormone angiotensin II. Angiotensin II increases blood pressure in several ways. It constricts blood vessels, promotes the release of vasopressin and aldosterone, and stimulates thirst centers in the brain to encourage water intake. Atrial natriuretic peptide, ANP, secreted by the atrial myocardium of the heart in response to high blood pressure. ANP reduces blood pressure in a number of ways. It directly dilates blood vessels. It increases glomerular filtration rate, thereby removing more fluid in urine. ANP inhibits the secretion of renin, and subsequently aldosterone. ANP also inhibits sodium reabsorption by the collecting duct. The kidneys control blood pH by adjusting the amount of excreted acids and reabsorbed bicarbonate. Plasma bicarbonate is filtered in the glomerulus during the first step of urine formation, then reabsorbed back into the blood in the proximal tubule. The amount of reabsorbed bicarbonate is regulated in response to changes in blood pH. It increases during acid loads and decreases during alkali loads. In addition, the collecting duct also generates new bicarbonate, which exits into the blood during high acid loads. The kidneys secrete erythropoietin, EPO, a stimulating factor for red blood cells formation. Low levels of EPO are constantly produced to compensate for normal blood cell turnover. When red blood cell count drops, such as during blood loss, the resulting oxygen deficiency state is detected by the kidneys, which respond by increasing their EPO secretion. The kidneys are also involved in calcium homeostasis. In response to low blood calcium levels, parathyroid hormone, PTH, stimulates the kidneys to produce the hormone calcitriol. Calcitriol promotes absorption of dietary calcium in the small intestine and increases calcium reabsorption by the kidney. PTH itself also causes the kidneys to retain calcium.